All right, welcome back, everyone. We're going to continue with this edition of PPML with the next invited speaker, Benny Pinkas. Benny is the head of the Cyber Research Center at Bar-Ilan University in Israel, and he received a PhD from the Weizmann Institute in 2000. He has worked since then on research in research labs like Intertrust Technologies, Hewlett-Packard, Google, and VMware. And his main areas of research are cryptography, computer science, and privacy, with a focus on secure computation. And yeah, we're very happy to have you, Benny, and of you all with private intersection analytics for machine learning. Thanks.
Hi, thank you for the nice introduction. So I'm going to talk, I worked a lot on private side intersection, and I tried to talk about its relation to machine learning. I'm mostly going to give a high-level description of private side intersection of PSI, high-level in the sense that I'll try to give like high-level strategic lessons I learned while working on this problem, try to relate them to machine learning. I will speak less about the specific techniques, but more about high-level lessons. Okay, but I'll start with specifics. Okay, so PSI side intersection is an example of secure multi-party computation, or MPC, which, I mean, this is the slide I always begin with. It began with the millionaires problem of Yao, which considered this mental game of two millionaires that want to compare, how much money they have without leaking any other information about X and Y. So they want to learn a single bit saying whether X is greater than Y or not. And this problem is very simple, but it's also interesting because traditional crypto doesn't help them in solving this problem. It can protect the communication channel from eavesdroppers, but does not help them do a joint computation. And Yao solved this problem. And essentially what he did is solve the general problem of MPC secure computation for any function. And basically what this does is that ideally, hypothetically, we could have a trusted party. In that case, the parties could send their inputs to the trusted party, who would send them the output. And in this case, if this trusted party doesn't cheat, they will learn nothing but the final output of the function. In Yao's case, it's a bit. In machine learning, it might be a model, etc. And what MPC does is to replace this trusted party with a distributed computation between the parties. So they don't have to trust anyone, but they want this protocol at the end of which they learn exactly the same output as the trusted party. Not more than that, and no other information about the other party's inputs. And of course, there were a lot of research about the right definition, etc. But this is essentially what's being done here. What's important to note is that MPC doesn't tell us which function to compute, only how to compute it without a trusted party. So basically, you should come to me, tell me, I want to compute this function. I realize that it's good in terms of privacy. We have differential privacy. If we release this model, then it's fine for ethical reasons, etc. The only problem I have is I don't have a trusted party to get the inputs and compute this function. In that case, MPC can get rid of the trusted party, but it cannot solve your other problems. It cannot tell you which functions to compute and about ethics, etc. So we're just in the business of getting rid of trusted parties. Now, Yao and afterwards others came with feasibility theorems saying that essentially any function that can be computed in polynomial time can also be securely computed in polynomial time, meaning securely computed. And this goes in the following ways. This results by Yao and Benno, Goldwasser, and Vigdazon, and Sham, Krepo, and Damgard, and Godach, Mikali, and Vigdazon, and others, and it started in the 80s. And basically they say, take your function, represent as a virtual Boolean circuit or arithmetic circuit. Virtual meaning that you're not going to implement this in hardware, but just represent the function as a circuit. And then they have a protocol to implement this circuit, okay? And this was initially considered theoretical, but in recent years, we implemented this and we worked a lot on trying to make this more efficient. And the reasoning is, why is that a good solution? Because complexity theory tells us that any function that can be run in polynomial time also has a polynomial size circuit representation. And the work of these guys tells us that we can have a secure protocol for computing a circuit whose overhead is linear in the size of the circuit. So from these two, we get that for every polynomial function, we also have a secure protocol that runs in polynomial time and implements it. So this is fine from a theoretical point of view, but then there was a lot of work trying to implement this more efficiently. But the main thing to remember for PSI is that the overhead of the MPC depends on the circuit size. Okay, it's going to be linear in the circuit size. Okay, so the takeaway from that work and work on generic MPC is that if something can be computed efficiently, we can also compute it securely and efficiently. And when we consider efficient, we should look at the circuit computing the function. And usually for real life, polynomial is not good. We want something which is very close to linear. So if someone has a linear size circuit computing it, then we can also efficiently compute it in practice. Okay, and then we get to the problem of private set intersection. So naively, for private set intersection, what we want to compute, we have two parties, and each of them has a set of names, say, and they want to compute the intersection of the two sets and leak nothing else. So this is the most simple version. First, there are only two parties, not more than two parties. And also here they want to know what's in the set, not just to compute the size of the set or another function of it, but just learn what's in the set. So as an example, well, here's an example. So one party is university, knows who works at the university and who studies there. Another party is some health ministry that knows who got vaccinated. And the university wants to know how many of the people in the university got vaccinated. So what's the probability, the conditional probability of someone to be vaccinated, given that that person is the university, is in the university. So basically, you want to compute the size of the intersection of these two lists divided by the number of people working in the university. So you want to compute a conditional probability. And these conditional probabilities, I mean, this is what, as far as I know, a lot of machine learning is doing. So you want to work with machine learning. So this is what we need. This is how PSI is useful. However, note that what we use here is not the intersection itself, but the size of the intersection. So ideally, the university doesn't want to know which of its students got vaccinated, say just to make a decision whether to open or not. It wants to know the probability of someone being vaccinated. So we want to know this size, not the names in intersection. So maybe for vaccinations, that's not the right example, but in many cases, we want to know sizes, not the intersection itself. And this actually makes PSI protocols more complicated because we have to hide more information. We have to hide the names of those in the intersection. And the other examples, so here's one example for multi-party PSI from the news. So there are people who go to many fertility clinics as donors, and then they end up, because they want to have many babies. And in the United States, everything is distributed. So they want to find out people who, were registered in many fertility clinics. And that's actually a real problem. Okay, and there are many other cases. So here we have many, parties, these fertility clinics. You want to find the intersection. And here you want to find the names of those in the intersection. And maybe you don't want to find someone who appears in all clinics, but if he goes to more than one clinic or more than two, then you want to raise a flag. Okay, so maybe you don't want to find the intersection of all sets, but if someone is in more than some threshold number of sets, you want to identify that person. And there are actually many examples of PSI, not all of them related to machine learning, but I'll tell them anyway. I'll spend a few minutes. So when you join a web app or say messaging like app like Signal, they want to compute the intersection between the contacts on your phone and the list of their users because they want to send messages to your contacts. So ideally, they don't need to get all of your contact list, just compute the intersection. So they were looking at private contact discovery. All browsers, this started with Google, do compromised credential checking, meaning checking passwords that you enter, checking if they appear in known databases of compromised passwords. So also here you want to do a set intersection between your passwords and those that appear in these databases. Okay, and here you have huge problems of scale because the databases include billions of compromised passwords. And this appears in all major browsers use this these days, as far as I know. Google published a few years ago that they use PSI to compute how much revenue they receive from ads. I'll describe this in a minute.
Alors,
And Apple recently described a system for detecting CSAM. CSAM is child sexual abuse material, child pornography in uploaded photos. So this system raised a lot of concerns, but from a technical level, what it does is computing the intersection between the photos that the user upload and a known database of CSAM photos. And if the intersection is larger than some number, 30 in that case, then they raise a flag, okay? So that's also an example of PSI used in the real world. Just more about Google example for computing ad conversion rates, which is described in this paper. So what happens there is that users register. Some Google know who they are, and then they see ads, say ad for ice cream, and then they don't buy the ice cream right away, and obviously they don't buy it, they don't buy and eat it on the phone, but they think about it, and then the next day they go and buy it offline, and naively Google doesn't know that this happened because they don't use any Google product. But Google want to know that this purchase happened because of the ad, because then they can charge the advertiser, tell him, look, see how much revenue you receive because of our ads. Okay, so for online purchases, that's easy, but not for offline purchases. And of course, I'm very naive. I don't know what they're actually doing, but this is like the big picture as far as I see it. So basically, what they want to do, and they had, a few years ago, they published an agreement with MasterCard about it. So naively, when MasterCard knows what I purchased and how much I paid, Google knows what ads I saw. So basically, they want to find those in intersection, and maybe they're not interested to learn, who bought ice cream and how much I spent on ice cream. They just are interested in computing the total revenues from ice cream by people who saw this ad yesterday. Okay, so what's important here is that they don't compute the intersection. So Google doesn't know who bought ice cream. Okay, and of course I don't know what they know or not know, but naively they don't know who bought the ice cream. They don't know how much each person spent. They just know the total revenue. So this is not computing the intersection. It's some function on top of the intersection. And you can think of other functions. For instance, maybe you want to add here some noise to get differential privacy. Maybe you just want to know if the revenue from the ice cream was more than $1,000 or whatever. Okay, and then of course there are other applications where you want to compute a function of the intersection. Okay, so basically, more generally, you want to do some analytics. Okay, so each item has some data associated with it. So like how much this is a purchase and how much I spent on ice cream. And then at the end, you get some function of the intersection and the items and the values associated with the items. And this could be, any function. Okay, so suppose we want to implement PSI. So the first thing, if you tell someone naive how to implement PSI, they will come with this solution. Okay, so they say, okay, to compute the actual intersection, Alice should choose like a cryptographic hash function, say like SHA, and she should send to Bob the output of this function of each of her elements. And Bob can apply this function to his inputs and just compare the output. So if some X is equal to some Y, then he'll see that they're the same. And since this is a cryptographic hash function, it cannot be inverted. It's one way. So giving this, Bob will not be able to invert the function and find what X is. So this is like this argument is indeed correct, but this assumes that the domain from which these items is small. And this system is insecure where the items have low entropy. So for instance, if the item is a credit card or phone number, you know that these values, these numbers, they come from a relatively small domain. So in that case, Bob can go over the entire range of credit card numbers or phone numbers, compute the hash of all phone numbers and compare it to this list. So then he'll be able to find out exactly what's in Alice's list. So this simple solution is insecure if the items come from a small domain or a domain with low entropy. And actually all interesting domains I can think of have low entropy. Okay, low meaning that brute force search can go over the entire domain. And actually there were, I think, commercial systems published that were using something like this, but that was quite a few years ago. So whenever you see a system and they tell you we don't use identities, we use some hash version of the identities, they might be using this. Okay, so that's insecure. Okay, so another option, I said that the guys in the 80s worked on generic MPC protocols. So you can try to compute the intersection using these generic protocols. So basically, we should design a circuit which computes the intersection of the sets, and then use any MPC protocol to implement it. Okay. The nice thing is that we don't need to know cryptography. We should download a library for doing MPC and just design the circuit. And any second-year student should, in computer science or engineering, should be able to design a circuit. Okay. The problem is how big that circuit would be. So a trivial circuit comparing two sets of size n, we have to do n-square comparisons, and when n is 1,000,000, that's too much. N-square is too much. And you can do actually more efficient circuits based on sorting networks, and then the size is going to be order of n log n. And for a while, this was more efficient than, this was like the most efficient PSI protocols, but now we have better solutions. So over the years, there were many PSI protocols. One group was based on public key crypto, and it was based mostly on the commutativity of Diffie-Hellman. And essentially what they did was an oblivious protocol for computing a PRF. So PRF is a pseudo-random function like AES. And an oblivious PRF is a protocol where one guy has the key and the other side has value X. And the guy with X learns the output of the function on that X without learning anything else about the key or about other outputs of the function. And a guy who has the key doesn't know anything about X. So this can be used for PSI. I'll show you in a minute. There's another set of protocols based on generic MPC and circuits, like what I described here, but they're less efficient. And there are protocols based on oblivious transfer and oblivious transfer extension. So the basic PSI protocol, okay, is this one, and it goes back to Chadwick Meadows in '86, and it's still used, like Google in their work. It was based on this protocol. So it goes like this. Alice has a set of inputs, both have the same inputs. Alice has a secret key alpha, and Bob has a secret key beta. Alice takes all of her inputs, hashes them using a, say, SHA, and hashes them, say, to a elliptic curve group, raises to the power of alpha and sends to Bob. Bob is doing two things. Takes all of his inputs, hashes them using the same function, raises to the power of beta, and sends to Alice. And also, all these values that Alice gave Bob, he raises them to the power of beta and sends back to Alice. What Alice is doing, she takes these values received from Bob and raises them to the power of her alpha. So she computes this. Now she takes these values she got from Bob and her value, the value she computed here. And you see that here, each item was raised to the power of beta and then alpha, and here alpha and then beta. So if some hashes were the same, you'll get equality. So Alice just needs to compare the two lists and she'll find what's in the intersection. So this protocol is actually very nice. It's simple to understand. If you didn't understand me, that's because I spoke too fast, but like if you spend 5 minutes, you understand it and you understand why it's secure. It's also very simple to implement. So you just have to compute, you get a library for doing, operations of elliptic curve, and you can implement this in, I would say in a few minutes, of course not, but that's very simple. Okay. It can be based on elliptic curve crypto, and actually it also have minimal communication, just send an elliptic curve element for each item. The downturn is that it has considerable computation because you have to do these exponentiations, like public key operations. And security assumes the participants follow the protocol. It's not secure against malicious adversaries that might behave arbitrarily. And also what you get here is that you compute the intersection and nothing else. Like other functions, it seems hard to compute them. So actually, in a very useful way, actually, you can change it to do some basic, variants. One is if Bob needs to learn the output too, then I should just send this thing to Bob. And more importantly, you can also change the protocol so that that Alice only learns the size of the intersection, not the items themselves. What Bob should do, instead of just sending this list to Alice after raising to the power of beta, it should shuffle the order. Then Alice will see equalities, but she won't know which items the equalities correspond to. So then she would learn just the size of the intersection. This is actually what is done in this Google paper of Ion et al. So that's actually very useful. So you can compute the size of the intersection, but more complicated functions, it seems hard to do. Okay. So about this variance, it's easy to compute the size. So you can do conditional probabilities. You can easy to compute sums of values associated with the items in the intersection, because you can associate each one of them with an additive lomorphic encryption of the value of the transaction, and then you can add everything. So this was done by the paper of Ion et al. That described the Google system. But to computing more complicated function, it seems hard. Like suppose you only want to learn if this section is greater than some threshold, or maybe perhaps you want to add some noise for differential privacy. You have to think how to do that. I'm not saying that it's impossible, but you have to hire a cryptographer to design a new protocol for that. So the takeaway from that protocol is that PSI is rather simple. You should take that protocol whose origin is in the 80s and just implement it. And but only for computing between two parties, not more than two parties. Now, more recent constructions observe that PSI is equivalent to oblivious transfer, and then just push it to do it as fast as possible. Let me go through this a bit quickly. So this is the DH protocol, and here's what you have. So this alpha, now we'll call it a randomization used by Alice, not a key. And beta will be a key of a pseudo-random function. And the function that Bob will use is like h of x to the power of beta. And this is a pseudo-random function. I mean, you can prove that. So when alpha sends these values to Bob, she randomizes them. And when Bob takes Alice's values and raises them to the power of beta, essentially he computes this PRF using his key. Okay, sorry, this is the PRF of Bob's inputs. This is the PRF, this is his key beta. And when he takes these values and raises to the power of beta, he basically applies the PRF to h of x to the power of alpha. Alice takes the alpha root, so this is essentially an oblivious pseudo-random function protocol. Alice will learn the output of the PRF on her input without learning what the key beta is. So essentially, this Diffie-Hellman-based protocol, Alice evaluates this oblivious, this OPRF on her inputs using a key that Bob has, and doesn't learn anything else. This is actually the reason why this brute force attack I described for the naive protocol, going over the entire range and computing the output, doesn't work, because Alice cannot go over the entire range of credit card numbers and apply H for them, because for every H, she needs to have Bob's collaboration to do this computation for her. So basically, Alice here learns the output of a pseudo-random function whose key is only known to Bob. So she cannot do a brute force search and go over the entire domain. Okay. So basically, what they did here is an OPRF. Okay, Bob has a key K, she has an input, she learns this output about her inputs, and he also sends her the output on his inputs. Okay. So we can think about using other OPRFs, which will be more efficient. Okay. So what we did actually in the early works was to replace the OPRF with oblivious transfer. So oblivious transfer, for those who are not familiar, it's a protocol where a sender has two values. The receiver wants to learn one of them, so he has input J, which is a bit, and the receiver learns XJ. Okay. So this is a protocol. I won't tell you how to implement it. The basic versions were implemented using public key operations, which are less efficient, but OT extension enables to do a few base OTs using public key operations and then do millions of OTs using very efficient symmetric crypto. Okay, so then OT becomes very efficient. So the Diffie-Hellman-based OPRF of the previous slides is inefficient because it's implemented using public key operations. So let's replace it with a more efficient OPRF based on OT. Let me skip this, how you implement it, because I'm not sure. But you can implement an OPRF using OT. So basically for inputs of length sigma, you'll need sigma 1 out of 2 OTs to implement the OPRF. Okay. And one other thing about this OPRF, it's only good for 1 invocation or 2 invocations, not for million of invocations. So for each key, you can only do like 1 or 2 invocations, not more than that Alice learns. Okay. So what we have with this function that the OPRF gives you a random output, but you cannot evaluate it many times, but it's also very efficient because you're using 1 out of the OT, which is very efficient. Okay. So we want to use it. Okay. So we want to compare large sets. Okay. So the OTs themselves can be computed very efficiently, but we would like to use, as few as possible. So naively, we have to compare n items to n items. Okay. So comparing 1 item of Alice to 1 item of Bob, it's sending sigma security parameters, say 40 or 60. So it requires sending like 60 bits. I didn't describe this protocol. Comparing 1 item to n requires n times n n times lambda communication, which is like 68 bits. Comparing n times to n require n squared times 60 bits, which becomes too large. So we want to make it more efficient. So one thing is to improve the OTs. And very nicely, so the original protocol that I skipped used 1 out of 2. So compare 2 numbers of length sigma, you needed sigma 1 out of 2 OTs. There are very nice 1 out of n OT extensions. The first ones were by Kolesnikov and Kumarasan, and then by KKRT. And they implement with the same cost of 1 out of 2 OT, they implement 1 out of n OT, where the server has n items and n can be arbitrary. So now to compare 2 items, we only need 1 out of n OT instead of like sigma, like the length of them, just 1. The way we do it, the sender has a large number of inputs as long as the domain from which the input comes. So suppose we're comparing 32-bit numbers. So here we'll have 2 to the 32 possible inputs. Okay, but you kind of compress all of them. The receiver has 1 32-bit number. At the end of the protocol, the receiver will learn this input that corresponds to his number and nothing else. And the sender can send to the receiver the input corresponding to the server's number, and the receiver can compare the 2. So this seems like magic. It indeed looks like magic. Is based on error correction codes, but it does 1 out of n OT, where n is like 2 to the 32 or 2 to the 70 with like the same overhead as the 1 out of 2 OT. So this improves how we compare 2 numbers. But still, we don't want to do n-squared comparisons. We want to do faster. Okay, so for this we use hashing, and the basic observation is that if they know a hash function age which they both agree on, and suppose this hash function maps an item to 1 out of n bits, and they both know this function. So basically, if they both have the blue item, they're both going to map it to the same bin because they use the same hash function. And the same for any item that they have. So now what they have to do is just to compare what Alice put in the blue in this bin with what Bob put in this bin, etc. So we have to compare less items. This orange item doesn't have to be compared to all of Bob's items, that's to what Bob put in this bin. So this is what they do. They map to bins, and then there's a lot of work to try to hide how many items they put in each bin. Because if we know that Alice put 2 items in the first bin and no item in the second bin, this leaks a lot. So there was a lot of work trying to hide this. I'll skip this, but using caching, we can do it. So, Without hashing, we'll need n square comparisons. With simple hashing, we can reduce it to n log n log squared n. With cuckoo hashing, we can reduce it to n log n or order of n. Cuckoo hashing with 3 hash function reduces the constants. And if we use cuckoo filters or something that we call oblivious key value stores, we can also get efficient security against malicious behavior. And this was over a few years. And it's not trivial, but not too complicated, but it reduces the overhead by a lot. Okay, so PSI between 2 parties can be very efficient. Okay, so now I'll try. Okay, so I described 2 solutions, and here are the the strategic information. What should we consider? Okay, so one thing is simplicity. Okay, so in the crypto, when I write a crypto paper, I want to optimize performance. This is what the reviewers are looking for. This is what interests me. But if I want to use it, okay, I probably need a solution that it's simple to understand because I need to implement it. Others need to help me implement it. And I also should be able to explain this to my managers. Okay, so it should be simple. Okay, and it should also be simple to implement. Okay, so Diffie-Hellman definitely fits this, much more than the series of works I described about OT-based. Okay, because this is, believe me, that is simple. Okay, now all these hashing constructions are based on using probabilistic constructions. Okay, okay, and sometimes a probabilistic construction fails. Okay, for PSI, a hashing failure results in either an inaccurate output because you couldn't put an item in the database, or some information leakage. Now, for some applications, this doesn't matter. So if you do machine learning over huge inputs, I think that if you have to, you cannot put in your set, you can have to ignore, just a few, like 1% of your inputs. Maybe that doesn't matter so much for the result of the machine learning. When I write a crypto paper, I want to make this failure probability extremely small. For machine learning, maybe if you lose like 1% of the items, that's not too bad. Okay. Interestingly, when Apple designed the system detection system based on PSI, the system, to make it more efficient, so they had a database of CSAM images. It couldn't fit all of it in the hash table, so it removed about 8% of the size of the original database from the hash table. So if someone has these photos, he won't be detected. Okay. But these are random and no one knows who these photos are. Okay, and so in that case, false negatives are fine. It's okay to ignore, like, if 8% of the database, and don't do anything if people have photos from that database, because usually people have a lot of photos. Okay, positive would have been very bad if someone who doesn't have a CSAM photo will be identified as someone that has. So this depends on the application. Now, if I want to do a theoretical analysis of a PSI construction, I want a negligible failure probability smaller than any constant, than any polynomial. If I want to do a concrete analysis, I want it to be smaller than some number, like 2 to the minus 40. Unfortunately, okay, so luckily, if you look at the graph of the failure probability, it's very sharp. Like, you have like a threshold, and immediately you go to this threshold, and the graph is amazing. But the guys who constructed these, hashing constructions, they don't have a sharp analysis for the failure probability. So they said that it's little O of 1. I didn't see, an analysis that tells me, exactly that, what the failure probability is, or that it's negligible. And at least for writing papers, we had to analyze it. So either we use the heuristics, or we do a lot of experiments because to verify 2 to the minus 40 failure probability, we have to do a lot of experiments, or we use some amplification techniques, but that's a huge problem. I guess that for applications, that's not such a big deal. So for applications, so typically it's very good that they have a very sharp threshold. You look at the graph, you know exactly what parameters to use. Something to note is that the failure probability of these hashing techniques is a function of the input size. So for inputs, it's something like n to the minus 3. Okay, This means that for larger inputs, you're going to have a smaller failure probability, which is great. But if you want to apply the system for small inputs, then you might be in trouble, because the system that has a small failure probability for 1 million inputs will fail a lot for 10,000 inputs. Okay, and you don't know what the constants here, so that's a problem. You should take a look at that. Okay. Another thing to think about is input size. So input size, okay, the OT extension is very efficient, but it does some pre-processing. If you want to do MPC for a PSI for small number of inputs, you might not want to run it, and their diffie element might be better. There's a nice result from this CCS of Michael Sulik and E3U that went back to diffie element based PSI, redesign it. So this is the overhead of their system. Okay, so this is OT based PSI that starts from some pre-processing cost. It behaves nicer, okay, but for small inputs, the pre-processing cost is more expensive than the initial cost. That is more expensive than the diffie element. So up to something between 500 and 1,000 items, it's more efficient to use their system than the ones based on using OT. I guess for machine learning, it's less interesting because we usually work with large inputs. Okay. Ignore this, okay? Because I think I started late, but I'm also running out of time, okay? Another thing is how to measure performance. Do we care more about communication or computation? So the Google result says, okay, we care more about communication than about computation, because in a data centers, we can put how many CPUs we want, but the channel here is more expensive. So we care about communication. The Apple system says the opposite. They don't say, but that's my interpretation. They say, okay, we do PSI for every image that the user uploads. The photo is a few megabytes long. If we add 3 kilobytes per item for the PSI, it doesn't matter anything for us. What matters much more is computation, because this consumes battery on the phone. Okay, so that's another. For other people, it's how much money they have to pay. So we can compare the relative cost on cloud services. So this is a graph we used one of the papers. This is communication cost. This is communication. This is running time. And these lines have the same price when you pay for them on a cloud service like Amazon's or Google. So for any choice on this line between communication and running time, you pay the same amount in dollars. And basically, you want to be as close as possible here to pay less. Assume, okay. Another strategic thing to note is semi-honest versus malicious security. So semi-honest, usually in MPC, you first get semi-honest security against adversaries that follow the protocol, and you have to pay a lot to get security against malicious adversaries. In PSI, the cost is very small for adding malicious security. It's like 10 or 20%. That's for the most recent protocols. So you pay almost the same. That's great. I have like 2 or 3 more minutes. So how much more time do I have? Minus 2 minutes?
Sorry. Yeah, I mean, accounting for the 3 minutes that we started late, like about 1 to 2 minutes. But
Okay.
it'd be good to have questions as well in that time. So.
Okay, so that's right. Okay. So if we look at the performance, this is the naive and insecure one. Okay, this is communication. This is runtime. This is exponential logarithmic scale. You want to buy here. This is the insecure protocols. This is the best how got to with OT and OT extension and hashing. These are the public key-based protocol diffie-Hellman with very good communication but bad computation. This is using circuits. Okay, OT has good communication runtime, but it's hard to implement and also hard to extend to other functions. Public key-based solutions have high runtime, good communication, very simple, and they can compute the intersection size. This is the best in terms of usage. You can use generic protocols to compute any function that you want of the intersection, but it's the worst runtime and communication. In recent years, I tried to push this as best as possible here, but we're still very far away. And the way we did this, we use all kind of OPRFs, FFTs, oblivious key value stores, whatever. A lot of work, but that's not the topic here. So what should we use? As I said before, Diffie-Hellman has the best performance for small inputs, easy to implement and explain, and can be modified to compute the size. OT, much more efficient for large inputs, but it's more complicated and it's hard to modify. And the dynamic protocols can compute arbitrary functions, but are much slower. What should we use for machine learning? I guess that the input sizes are large. Perhaps we don't care much if a probabilistic construction ignores some items or leaks some limited information with very low probability and very limited information, but it's very hard to quantify this. Perhaps we can use sampling and differential privacy to sample a small set after the large set and then work with that, but it's very hard to quantify what you do there. And this depends a lot on the context, okay? So real applications are different than crypto papers where we have to prove everything and we just look at performance and nothing else. Just one word, there's a different model which I haven't discussed. If you have a lot of users, one possible model is that each one of them shares its input between, say, 3 servers so that none of them learns the input. And then as a service, they run the PSI between these users. They can compute the intersection or items that appear in more than 3 or 5 items. And this can be very efficient, requires a different trust assumption, but that's a whole other talk, okay? And, papers and conclusions, basically here. MPC is useful, but there's no silver bullet, okay? And I'll stop here and I'm happy to answer questions.
Thanks a lot, Benny. So in the benefit of time, we'll have just one question. And Olia asked that she was wondering about PSI integration in secure computation and whether there are different PSI protocols depending on their end use case. So I think that kind of answered that in the last few. But I like your point about integrating in a bigger MPC protocol, and that probably has to do with in which form the output is given, right?
So the naive PSI problem, one of them learns the intersection. Okay, it would have been much nicer for them maybe to learn shares of the intersection or something like that. Shares of the size of the intersection, that's probably easy. That's easy. For more complicated functions, we had this work on circuits where then they compute whatever function they want, but that's more complicated. Or you can go to this model. In this case, they can compute whatever they want on top of the result of the intersection.
Yeah, and then just very quickly, Rakyong mentioned homomorphic encryption and whether PSI protocols based on HE where are they placed in your kind of organization?
So there are PSI protocols based on homomorphic encryption. I guess it's more like it's like this OPRF that you basically implement OPRF with the homomorphic encryption. As far as I know, Microsoft protocol for compromised credential checking, for checking if my passwords when I use Edge in these databases is based on homomorphic encryption. Okay, I think that using OT is going to be more efficient, but you can certainly use homomorphic encryption.
Interesting. All right, so let's thank Benny for the talk. Thanks a lot, Benny. And now we'll move on to the next contributor talk, Sidon.